So welcome everybody to this first really scientific session. We have two exciting speakers talking about new developments to take cryo-EM into new dimensions in a way. And the first speaker is Davide Tamborrini from the Biozentrum in Basel, who will talk about ray and drop.
Hi everybody, thank you for the nice introduction and thank you for having me here. Really cool, really excited to share with you the raindrop. So let me first guide you into the thought process that led me to work on this in the first place. So I joined Ben Engel lab, where we really like to study photosynthesis, as you can possibly already see in this picture. We like to be surrounded by green. And in fact, I will start with some acknowledgement, and especially I want to thank Simon here, Fanny, and Sophie for helping me out with some of the data I'm going to present. But going back to the narrative, when I joined the lab in Ben, the scientific question I was trying to tackle is how thylakoid rearrange during the dark to light transition. And the idea is that we want to study the effect of protomotive force, and we want to understand how the thylakoid architecture and function relate. So again, the idea is to use cryo-electron tomography to gain 3D information on the architecture, so to really have a structural understanding of it, and also to have some kinetic. So the idea is to use the lumen swelling kinetics as a proxy for ion osmolarity in the lumen. So to do that, you can imagine that the biological question is clear, but in fact, this leads to another question a priori, which is how we can control the light, and specifically its intensity, its timing, and the spectrum in the last second or the last milliseconds before plunging. And the answer is quite naive. We need to build a light plunger. And sure enough, when I started looking into this, I thought that this could not possibly be the first time somebody needs to build a light plunger. There must have been other cases, and sure enough, when I looked back in the literature, I could find examples already in 20 years ago when people were using flash-induced photolysis. And throughout the last 20 years, there have been plenty more examples of light plunger that have been built. The last one I just want to mention is from Charité group, where they use infrared sensor to determine when the plunging was happening, so they could time the light flash. So it seems that the issue of building a light plunger is not new, and in fact, probably the issue we have is not that we cannot build a light plunger, is that most of the time we come up with the bespoke solution that specifically work for our scientific question on our instrument, and that are not easily transferable or reproducible. So the goal that I was trying to tackle again was to build a light plunger myself. And initially I was going with a solution such as this one. We had this custom light plunger in the lab. And oh, I see, I'm one slide ahead. Okay, here. We had this custom light plunger in the lab. Yeah, and I was about to work on this one with the idea that we could transport it across the institute, then we could plunge in the institute and we can reproduce our experiment across different labs. However, this actually is not an advantage, it's a disadvantage, because if you think about it, we already have plungers in all the cryo-EM lab, more or less, and these are commercially available plungers. So a very better approach would maybe be to engineer a device or a platform that can be used on all these plungers, so that we don't have to reinvent it every time. We would have something that is plunger agnostic and more portable. And in fact, in the spirit of making this reproducible and as useful as possible, I also try to think of all possible other experiments people would like to carry out with a light plunger. And of course, the list is not short. Some of them are already being used, like you might want to photo uncage your ATP or your GTP or EGTA or whatever. Maybe you want to do some photosynthetic studies on PS1 or PS2. Or maybe you just want to look at organelle and cellular responses. Specifically, you might want to pace muscles, or you might want to trigger neuron, especially going into the cryo-ET as we are doing more and more. So we had some requirement to try to fulfill to make this device as useful and as accessible as possible. So we want to cover multiple uses across labs. We want to have multiple scenario support, so LEDs, but also lasers, and also possibly other devices that are not either a laser or a LED. We want to make it accessible, modular, and easy to extend by design. And as I already mentioned, we want to have cross-platform compatibility. And of course, we're going to try to have everything as shareable as possible so that other people can expand on this platform later in the future without needing to reinvent all these steps once again. So the core idea is not to build a light plunger, but possibly to build the last light plunger that we really have to come up again. So in order to try to stop reinventing the wheel, we really need 4 building blocks. The first one is a microcontroller. We need to control the different events, and we need a timing logic. So that would be a custom printed circuit board you can see here. Then we need to talk to the different plungers. So we need a universal system to interact with all of them. And to do that, we can simply pretend to be a foot pedal. So we would have a relay in the PCB that will close the circuit. So all you have to do is to unplug your foot pedal, put the device in, and it should be non-invasive and easy to remove. And then we need to link the first event to the actual plunging event. Because of course, depending on the device you're gonna use, you're gonna have a delay that might be second or millisecond. It will depend on the program you're using, of course. And you really want to have millisecond accuracy on this device. So what you do is that you can detect using an accelerometer and a radio transmitter mounted on the sample, so in this case, on the tweezer. So you can directly have a millisecond readout of when the plunging event is actually occurring. And finally, you need to deliver the light. So it might be easier scenario an LED, slightly more complicated if you want to have a laser, you might need a more complex system. So for the next 10 minutes, I'm going to try to cover these examples. The first one, these blocks. And the first one is a microcontroller. Here, it's a design of the microcontroller that really doesn't need to be understood by any user, but I'm simply putting it here because if you want to build on top of this will be accessible. So you can have easy access and you can just modify it as you wish. And the other reason I'm showing this is that I'm going to cover LED and laser as perturbation. But in fact, we're going to leave a lot of exposed pins here that can be used to interact with other machines you might already have in the lab if you want to use other type of perturbations for your sample. So next up, we have to detect the event I was mentioning. So all we need is really an accelerometer and a radio transmitter that together with a small coin cell battery we can mount onto the tweezer. So here is an example of the GP2 tweezer. Really, all you have to do is to stick it on it. In principle, if you have a 3D printer, you can also 3D print a support to make it look nicer and more reliable. But otherwise, all you need is really a piece of tape. And in fact, the example I'm going to show here are just taped on devices. Same goes for the VitraBot. So again, I'm covering these 2 cases because they're the most common accessible plunger, but if you had other, you could just design or attach it to the tweezer, so it would always be relevant. And again, here is a simple comparison of all the work you have to do is take the tweezer and stick with some tape your sensor on it. Finally, we need to deliver the light. And again, the easier approach is to use a LED. You can buy this off the shelf. You can just decide the wavelength you need, but then you need to point it to your sample inside the chamber. So here I'm showing the GP2 example where you just have a 3D printed adapter, and the VitraBot. Really, the simple case is off the shelf a star PCB with a LED. Alternatively, where you mount it on the adapter, and in the chamber it looks something like this, where you have your sensor and your LED pointing to the tweezer. However, again, we try to lower the entry barrier to this kind of experiments. So we also provide I couldn't help but putting my name on it. But we also provide PCB with multiple LED that comes by default. And again, you can just download the Gerber file and send it for production, and you will get it in your office within a couple of weeks. There are default wavelengths, and they are all, and there are 2 different types of pulses you can use depending on the experiment you want to have. However, in some cases, 50 microseconds might not be enough. It might be too slow for your type of experiment, so you really want to go for a laser. And if you go for a laser, you need to find a way to deliver the laser. And of course, you do that with an optic fiber. And really, then again, you have the barrier that you need to build a fiber injection module. And also in this case, we try to lower the energy entry so that you can just simply use off-the-shelf Tor Labs component to build this device. You can probably build it in 5-6 hours and then calibrate it into the last hour. And all the instruction will be deposited on GitHub as well and in the paper once we submit it. Really, the only thing that you might want to modify here is the adapter that allows you to mount any type of device you might have in the lab. This is a 3D printed component. And the hope we have is that, well, we provide a few examples already for commercially available lasers, but the hope is that if you use a different device and you produce your own customized adapter, then you would deposit that too, so that other people can simply download and print it. So it looks something like this eventually. And we can also provide a few examples of off-the-shelf diodes with custom drivers so that we can achieve alpha microsecond pulses. We need, of course, to deliver this light into the chamber, and then we therefore have a collimator. You can also just have the fiber getting into, but if you want to have higher fluency and irradiance, you just might want to use a collimator. And once again, this is off the shelf. The only part that you will need to adapt is the adapter, which we provide for both GPT and VitroBot. And then this is what it looks like. So here you have the GP2, where it's on the side, you have the optic cable coming out and the VitroBot. Or if you have a custom plunger, you can just drop it on the side. When it works, it looks something like this. Here, I'm just having a few pulses in a dry run with a red laser, or in the Leica, again, similar idea. So I show you so far that we build a platform to deliver light doing plunge freezing with millisecond accuracy and with duration that can be controlled depending on the light source, together with intensity and spectral composition. And eventually all you need is this device. What is really important now is trying to have it easy to obtain, easy to install, and to use. Again, you don't want to have the skilled postdoc that is specifically working on this project that then leaves the lab and with him dies the knowledge. You want something that everybody can use repetitively without losing continuity. So to prove that this is exactly the case in this device, and that this is what we really strive for, I'm gonna just, the idea is that, usually you have something like this in your abstract where you have a compact, elegant, and high-performance device, but then in reality, you end up with something like this, and really want to prove that this is not the case. So here is a simple 10-minute plug-in of the device. So I'm showing the Leica as an example, and you can see the Leica with its foot pedal. We bring in the device. We just have 3D print the cover, and then we can remove the foot pedal and connect it directly to the raindrop. Then we need power control, power support for the unit. So we connect to power. We connect the light. We put inside the chamber, and then we connect to our device, where we can later control the experiment. And of course, this is messy, and since we are 3D printing a lot of stuff, we might just as well 3D print an adapter, so we have it on the side, and it's nicely organized. So the last bit we need to control this again, and to make it easy to access is a GUI, of course. And the graphic user interface looks something like this, where you can select the type of plunger you have if you want to, otherwise you can just directly run it independently. You would have a selection for LED or laser, or if anybody comes up with additional perturbation, they would just add it to the pack. So you decide what type of perturbation you want, how long you want it, when you want it. And then you're gonna be shown with a timeline of your experiment here. And the timeline looks something like this. And this is also useful to understand how the device works. So what we're really doing is to trigger the relay, pretending to be the foot pedal, and then wait a X amount of time until the plunger does what it needs to do. And the first event that then happens is the T1, when the tweezers start falling. And then they have a fall of about 100 milliseconds, will depend on the plunger. And then they fall, and we have T0, which is when they are hitting the bottom. We can detect both of these events because we have the radio signal. And next, what we have to decide is whether we want the event, the perturbation to happen during the drop. In this case, is I think, yeah, it's a 30 millisecond pulse during the drop, or maybe you want to happen before the drop, or even before you trigger the relay, maybe if it's longer than 30 seconds or something like that. So here are two examples. Here we use the laser, for instance, that we wanna have a 200 millisecond pulse, or we can use the LED and we have a 30 millisecond pulse during the plunge itself. Of course, this would require you to adapt the positioning, either you're illuminating the entire chamber, but if you want to collimate it, then you would have to adjust the direction of your beam on the sample as it falls. And the idea is that you have a planned experiment, but then the GUI is also giving you the actual reading it gets from the light plunger, because there will always be some mechanical delay, especially if it happens before T1. So then you have your data. All you have to do is to upload to, well, there's an inconsistency in the name I noticed this morning, but yeah, you have to upload it to your device, and then you have to start it. And ideally, you can also save all your metadata regarding your experiment. So again, you can share them easily and you can keep track of what you've done. Yeah, last thing I want to show is a an example of such a protocol. So here, what we did was to mount the radio and the sensor on the tweezer, and this really takes like a couple of minutes. Then we use LAD. We start our procedure. We apply the sample, which I actually forgot to upload here, but then we trigger it, and here we're doing a 30 millisecond pulse just before freezing. And hopefully you can also appreciate that this is not really taking much space, so you can keep loading your sample in a pretty convenient way from the side entry. Right, so back to this slide again. I hope I could convince you that this was, yeah, that this is hopefully something that is easy to work with, and that is a platform that might serve as a building block for more additional type of perturbation in the future. Again, we try to cover as many as we could. But going back to our biology, what we wanted to do is to study the thylakoid, right? So I'm bringing here one biological validation that we had. Is very preliminary data, and it's on the long term of the exposure window we can have. And what we want to see is how the thylakoid swell during dark light. So we can do cryo-electron tomography, of course. We can look at the membrane segmentum, and then, yeah, I will skip this. But we can look at the membrane segmentum, and then using Ben-Barad morphometric, we can measure the distance between lumen and within the lumen. And the results look something like this. I really, again, thank Wojtek, Fanny, and Sophie for speeding up the results on this side, so I could present it to you today. And in our condition, we just use the PCB here, and because we don't really need to be collimated, you can just stick it on the side, so the entire chamber is illuminated, and it takes even less time to mount it on. And then the protocol was an illumination of either 0 second, 1.5, 6 seconds, or 30 seconds. And here you can see different readout. Each time point is a membrane pair, and each tomogram is color-coded. And you can see how the thylakoids are swelling their lumen, going from dark to light. And in fact, this gives us some statistical, still statistically poor, because again, it's preliminary, but we clearly get an increase in the thylakoid swelling. We observe up to 30 seconds, and we can fit a one-phase rise model where we can tell for the first time kinetics about this event, a light-induced event. So we can now see that the tau is about 7.58 seconds. So with this, I'd like to conclude. If you want to give a try to this, we hope to soon release it and make it open. But if you want to be an early tester and want to give it a try, we have spares in the lab, so we'd be happy, especially if you have a facility and you know that this might be of interest of some of your users. Yeah, just drop an email and we'd be happy to share. It would be also good to know whether it is working as intended and you can have easy access to it. With this, I conclude. I'm happy to take questions, and thank you for your attention.